So first of all, I'll explain to you what we mean by the diffraction of light. Okay, then I'll go to diffraction grating and an experiment related with the diffraction grating. Okay, so this is our slit. Slit means a narrow opening. The opening is from here to here, right? And the size of the opening is approximately with the size of the wavelength. The size of the opening is approximately to the size of the wavelength which is used, and we're using monochromatic light. Monochromatic means a single wavelength. Now these are the wavefronts. These are the wavefronts. Okay, wavefronts going to incident on the slit. Then here it is a screen. Okay, so this is our screen. On the screen, what we expect? Normally, if there is no diffraction, then we expect the image of the slit only. But as the diffraction is there, because of the diffraction, there is again an image of the slit, but it is very dim, okay, very faint. And again the size of the slit is here again. It appears here also. No doubt it is also dim or faint. So that means spreading of the light in the region of the geometrical shadow. Well, there should be shadow. There should not be anything. But again there is an slit. There is an image of slit at here. There is image of a slit at here. So that means the light spread into the region of geometrical shadow. This is known as diffraction, and only condition is the size of the opening should be small. And why happens the okay, you notice this point will be very bright. Why? Because the wavelet which are coming through beam number 1, the wavelet which are coming and reaching here through beam number 1, and the wavelet which are reaching here, which are coming through beam number 2, they are in the same phase. They are in the same phase. Mean crest on crest and trough on trough. That means maximum intensity. And why it is minima here? The reason of this minima is that the wavelet which are coming through beam number 3, it is of this shape. Okay, and the wavelet which are coming through the beam number 4, it is of this shape. What happens? Crest and trough, when they fall upon one another, crest and trough, they cancels each other. Cancels each other means becomes minima. So this is minima, this is minima. This is called first secondary maxima. This is again first secondary maxima. This is primary maxima. So primary maxima, secondary maxima, secondary maxima. So this is the diffraction. So what is the diffraction grating? Diffraction grating consists of a series of parallel slits. I mean, just look. We are looking some lines here. So there are some transparent lines, then an opaque portion, again transparent, again opaque, again transparent, again opaque. So in this way, It is a series of slits through which the light can pass. Mean, like this is an opening, then opaque, but through light can pass. Now light again can pass through this portion. Again light cannot pass. Again the light can pass. Okay, again the light cannot pass. So the very large number of slits, okay, parallel slits. This is called a diffraction grating. Guess what would be the size of this narrow opening? Guess what it is. Can you guess the size of the slit? No doubt there are many slits, but what about the size? Now I will discuss with you what is a grating element. Grating element. Okay. Now this is an opening, and this is the opaque portion. Light can pass through it, but it cannot pass from here. Again the light can pass through this portion, and again it is an obstacle, opaque portion. So this size is A, this size is B. Again this is A, and this one is B. Now grating element, or what I can say, from center of center of this opening and center of this opening. This is called grating element. Now the distance between the slits, distance between two slits, neighboring slits, that is called the grating element. From here to here, the distance is A plus B. From this center to this center, this distance is A plus B. This is called grating element. This is a laser light. The laser light is coming from this source. Let this light is red in color, monochromatic. Then we are having a diffraction grating. Then this is a screen. And what we are getting on a screen? We are getting the central maxima. This is central maxima. Then again secondary maximus. First secondary maximus. Central maxima. First secondary maxima. Second secondary maxima. And so on. This happens if the laser light is thrown on a diffraction grating. We'll get a diffraction pattern. So now here I'm having a double slit. Like this is opening, this is opening. The wavelet is going from here on the screen. Wavelet is going from here to the screen. The difference between this path and this path is this one. Okay. And if the path difference between the two, it is lambda, 2 lambda, 3 lambda, then there will be constructive interference, maximas. We get maxima on the screen if the path difference between the two is lambda, 2 lambda, 3 lambda, like that. Or if path difference is 0. Okay. Now if this angle is theta, then this angle will be theta. Right? So this is a baseline. This one is perpendicular. This is hypotenuse. Okay? And perpendicular upon hypotenuse is equals to sine theta. What is perpendicular? It is n lambda. What is hypotenuse? This is d, is equals to sine theta. That means n lambda becomes d sine theta for maximas. So we get maximas if this condition is fulfilled. Okay, mean if the additional path between the two beams, beam 1 and beam 2, if the additional path is equals to n lambda, then it will be constructive interference. And this perpendicular is basically d and of sine theta. So if I'm having double slit, then from these two slits, there will be interference as well as diffraction. Now this violet color, violet color amplitudes, they are because of interference. Then this, blue color pattern, it is because of the diffraction through the single slit, like this. Now because now interference and diffraction both will happen, now we'll get an interference pattern in the diffraction pattern, like together. This red line, this is because of interference. So interference pattern will get interference pattern in this diffraction loop. This is diffraction pattern, and in that diffraction pattern we are getting interference pattern. So this is what we'll get. So if this is first secondary maxima, okay, this is again first secondary maxima. So what is the condition for first secondary maxima? That it is n lambda is equals to d sine theta. For first secondary maxima, n equals to 1. So lambda equals to d sine theta. So this is the formula for first secondary maxima from the central maxima. Okay. So this is basically a source of light, mean laser source. The laser which we are using, that it is red in color and having the wavelength, I think so it is 650 nanometer. Okay. Then we are having a grating. So this is a grating. And here we are having a screen. The laser light is shown on this, diffraction grating. This is diffraction grating. And 15,000 lines per inch. 15,000 lines per inch. This is the specification of the grating. 15,000 lines per inch. Okay, laser light is shown. Now here we are having a screen. On this screen, this is central maxima, first secondary maxima, and again another first secondary maximas. And I think the distance of first secondary maxima, if you take this distance as well as this distance, then take the average, and I think so this average distance is 5.7 centimeter. So this is actually why. Okay, because we do need sine theta. So if this is y, and from screen from grating to here, the distance is capital D. Okay, and if this capital D is in our case, in my case, this is around 15 centimeter. Okay, then you can find what is sine theta. Okay, this is 5.7, this is 15 centimeter. So it is clear now that this distance y, okay, it is roughly, I think so, 5.7 centimeter. So central maxima, first secondary maxima, again first secondary maxima. Now using formula that because our maxima is first order maxima, 1 lambda is equals to d sine theta. You find lambda from here. Now what about the d? You know, you are having 15,000 lines per inch. Find out what about the grating element, means small d in, you know, centimeter. Okay, mean what is one line? One line is equals to, convert this inch into centimeter, and I think it is 2.54 centimeter divided by 15,000. That becomes the grating element small d. Small d is 2.54 over 15,000 in centimeter. Then using sine theta. Sine theta is perpendicular over hypotenuse. Perpendicular, I think it was 5.7 centimeter. I think so. And capital D, it was 15 centimeter. And then your lambda will come in centimeter. Then convert it into the nanometer. And write me that value in the comments box, what it is.
Christina, I see you're showing off your lateral thinking again.
Actually, this is a different experiment. So I'm using a diffraction grating here, and it's a nice compact arrangement if you haven't got very much space per student in your lab.
Yeah, very clever, and it looks a lot safer because the laser's pointing downwards.
Yeah, that's true, but you must point out to students that they might get stray reflections in this plane.
Yeah. So this works in a similar way to a double slit, but the physics is slightly different, but I'd expect teachers to teach it around the same time.
Yes, the relationship here is n lambda equals d sine theta. So n is the number of the order of the fringe that you're getting. Lambda is the wavelength. D is the spacing of the lines on the diffraction grating, and theta is the angle between the straight through direction and the fringe that you're looking at.
Yeah, but these are quite big angles, so students can't get away with using a small angle approximation for sine theta.
No, that's right. They should use trigonometry to get theta.
Okay, well, shall we give it a go?
Yep. So if we take two fringes either side of the central maximum.
Yeah.
And there we go. 191 millimetres.
Yeah, but we're going to divide that by 2.
Yes, that's right.
Okay.
And then the height, the distance to the screen, taking it from the, okay, is that straight? Yep. 225 millimetres.
Yeah, and how many lines on the grating?
300 lines per millimetre. Okay.
Okay, so if my calculations are correct, that gives us a value of 650 nanometers, which isn't bad for red light. And if I was doing this with my students, I'd get them to compare their value with the manufacturer's stated value.
Yes, and if you wanted to take this further, you could give your students a different diffraction grating with a different number of lines per millimetre, if you've got them, and challenge them to compare the uncertainties they get for their values of wavelength.
Brilliant. Thanks, Christina.